Hello guys, my name is Engineer Steven. I'll be taking you guys phase 1 to 4, and based on the class we have done earlier, I taught you guys electrostatics and Gauss law. So today we'll be moving to electric potential. If you have any question at all based on those other topic I taught, you might just go on the comment section and type in there. When we get on, when we see the questions, we'll be able to answer it. Then for our topic today, electric potential, I'll be teaching you guys electric potential, the introduction. First of all, the work done that exists between a charge, the work done that exists in a moving charge is referred to as the electric potential. Take notes, the force that exists on a body that exhibits electric potential is usually conservative in the sense that energy is not lost to the surrounding, something like that. Then I'll be moving to electric potential energy. Electric potential energy is the amount of energy required to remove a charged body between 2 point surfaces. Like, assume this is a particular body A and this is another body B. Assume the charge here is Q, the reference charge, and this is the point charge Q naught. The electric potential that exists between these two bodies is the work done that is required to move the charge from this point to this point. Take note, whenever a reference charge and is interacting with a unit charge, and when they are placed in this kind of condition, it always experiences a conservative force. Let's call the force F of A, assuming the distance from here to here is equal to RA. Then let's bring another point charge. Let's place them. This time this charge, the distance between each other is reduced, assuming we are trying to reduce the distance between them. This one is equal to RB. The conservative force here is equal to FB. Let's call it FB. Take note, when the charge particle, the more the charge particle is brought closer to the reference charge, or the unit charge is brought closer to the reference charge, when the thing is closer, the conservative force is usually more stronger than when it's far apart from it. And the normal formula for the work done for this 2 point charge, or for the point charge when it moves from the 2 points, when it's moved from A to B, is equal to U of A. That is the potential energy of A minus the potential energy of B. And this can be written in another sense, in that I can take this guy forward and bring this guy backward. I can also interchange it by writing it this way. It's just the same thing. I just brought this one back. Then from there, if I bring out a minus sign, I'll be having U of B minus U of A. This is the electric potential energy. that exists between 2 points. It can also be written in this form, minus delta U. So from there, remember that in a uniform electric field, that the force acting on the uniform electric field is equal to Q naught times A, where this is our electric field intensity and the Q naught is the test charge, or rather is the test charge. So if we want to imply this one to this equation we just did here, I can now simply write, since we know that work done is equal to force times distance r, and this change in electric potential energy is also equal to the work done. I can write this formula in a similar way by just placing this one here to now be minus the minus sign Q naught A bracket U, rather U is the energy, but this time we'll be using our arrow B minus arrow A. So this time this will now be the formula for solving the work done, or the electric potential energy for the system. Then another formula for solving the electric potential energy is this. Our U is equal to the integral arrow B over arrow A. This time the electric potential energy for the diagram I drew earlier, that involved 2-point charge AB, one arrow A and the other arrow B. This time the charge was brought closer to this point. The change in the electric potential energy that exists between these two diagrams I drew here is what I'm trying to calculate here. So is what I calculate at this part actually. Since we are dealing with electric potential energy and is equal to the work done, which is therefore equal to arrow B arrow A. The work done is equal to the force times the arrow. So from there I can bring out this F, since we are just interested in the integral of the arrow. I can bring out the F. It will now give us F Q naught, the reference charge and the test charge, divided by arrow square, the integral of arrow B arrow A, the arrow. For me, I can take the arrow square here. It will now be equal to K Q naught integral of arrow B arrow A, the arrow over arrow square rather. If you integrate this, you will end up having this as your answer. As the value for the change in electric potential that exists between the two systems that I drew earlier when the point charge is then shifted closer to the reference charge, or the test charge is shifted closer to the reference charge. Then several things were expected to note when it comes to electric potential energy, that the electric line of a force is usually conservative in the sense it's conservative in the sense that the electric potential at a point at any closest instant is equal to 0. And also the electric line of a force at a path, let me assume this is a line, or the work done by an electric force along a path depends solely upon the end point, this point and this point. So those are the several things you have to note when it comes to electric potential energy. Then the superimposition principle applies to get the net potential energy. First of all, we know that when it comes to energy or work, energy equals to work is equal to the force times the distance, r, normal. And our force from electrostatics is kq, let's assume this is the q naught, the test charge, over the r square times this r. This arrow can cancel out this arrow, be left with just one arrow. So now be equal to kq q naught over r. So from there, in the presence of several charges, if we want to now determine if there are more than one charges, then you now apply the superimposition law, or the principle that applies for this potential energy. Then you now say that sigma, carrying this k outside because the k is constant and this q naught is always constant. Then for i not equal to, or rather for I equal to 1, we'll now have it that q1 or rather qi all over r raised to power n. So the summation of when kq naught, the summation of when qi over rn will give us the value for when it comes to several charges relating to each other. That is, I can write this thing in this form also, kq naught bracket the big q1 all over r1 plus the q2 all over r2 plus qn all over rn, something like this. Then our next subheading is the electric potential. Electric potential is usually represented as electric potential is usually represented as V. That is the SI unit of the electric potential energy. And take note, electric potential energy is a scalar quantity. It's not a vector quantity. It's usually asked question in the examination. What quantity is the electric potential? Vector or scalar? Is a scalar quantity, in case you are asked. Then the electric potential is the ratio of the work done on the charge, the ratio of the work done on the charge divided by the charge itself. So I can say electric potential is equal to V is equal to W all over Q, which can also be written this way, where we know that our W is equal to the force times the distance all over Q, where our F is equal to KQ all over R squared times R. Our F from normal electrostatic law, this one can cancel out this one, we'll be left with just one arrow divided by the Q. So it will now be equal to KQ smaller q over r divided by the q. It can also be written in this form. It will now be kq small q over r times 1 all over q. This one can cancel out this one. So we'll now find out that for electric potential, our V is equal to kq all over r. It will now give us kq all over r. Our V is also equal to E all over D. That is to say, the electric field intensity all over the distance between the plate is also another way to calculate the value for the electric potential. So if we want to represent this one now, when there are several charges present there, in the presence of several charges, if we want to represent it based on superposition law, I can just write it in this form. Just write it in this form. So now since our V is equal to K just 1Q over R, I can say V is also equal to the summation I equal 1 Q, okay, I equal 1. Bringing out this constant, we'll now be left with Q I all over, let's call it ROJ, which can also be written in this form: K bracket Q1 all over R1 plus Q2 all over R2 plus up to the Q of I all over the Q of J, or the R of J rather. So this is the several form to get the superposition principle when it's applied to electric potential when there are presence of several charges. Then equipotential surfaces, it could be metal, any substance at all. There are substances that exist at equal potential. There are substances that exist at equal potential. That is to say, the work done between any 2 points on a equipotential surface is equal to 0. In an adjacent equipotential surface, in the presence of an adjacent equipotential surface, when one part is more equipotential than another part, there is a possibility that the charge from the part that is more equipotential might just migrate, something like diffusion or osmosis, where it will migrate from the part where there are higher concentration of charge to the part where there are lower concentration of charge, in order to stabilize a more equipotential surface. That is to make sure that the surface is more equipotential. So that is that for that. In my next video, I'll be solving some of the calculation that involve this electric potential on our platform. Thank you.